Hey guys, and welcome back to this class, Data Science Logistic Regression in Python. So as a lead-in to the logistic problem, we're going to talk about how to calculate the likelihood for a bias coin. So we have a coin which has a probability of heads equal to P, so it's unknown, and the probability of tails is, of course, 1 minus P. So we're going to do an experiment to help us determine P. We flip a coin 10 times and we get, say, 7 heads and 3 tails. So how would we write the total likelihood, which is the probability of seeing the result that we saw? So this is just if the probability of heads is P, it's P to the 7, and then the probability of tails is 1 minus P 3 times. So we can do this because each coin toss is independent, and so we can multiply each individual probability. Now what we want to do here is we want to maximize L with respect to P. So we want to choose a P that maximizes L. And of course, to do this, we can use calculus. Now, most of these problems, we take the log and maximize the log likelihood, which is acceptable because the log function is monotonically increasing, meaning that the point at which the likelihood is maximum, the log likelihood is also maximum. So let's do this. So we take the log likelihood, which is we use the multiplication rule. The power rule. Here we set the derivative equal to 0. And we solve for P. So we get P is equal to 7 over 10, which is the probability of heads, which is what we expect. So now let's apply a similar idea to logistic regression. So we have the probability that y is equal to 1, so we can think of that as heads. It's equal to the sigmoid of the inner product of w and x. Usually, to be more succinct, we just call this y. So our likelihood would look like this. So if we have n samples, right? And so it works if I write it like this, because if the target is 1, then our probability should be y, and if the target is 0, then the probability should be 1 minus y. Now what's interesting about this is if we take the log likelihood we get the same form as the cross entropy error function that we talked about last time. They're just negatives of each other. So, in other words, maximizing the log likelihood is the same as minimizing the cross entropy error.